We now continue our discussion of steric strain and how it affects the shape of molecules. Our learning goals for today are to understand how torsional motion provides a really important means for relieving steric strain. And we're going to use Newman projections, this is a new topic, to represent these torsional conformations. So it's a simple way to represent the shape of a molecule. So how do molecules respond when they have repulsive interactions between two atoms that are getting in each other's way? So I'm drawing this from the end. We're looking down a carbon-carbon bond, and each of the carbons in this bond are attached to some big bulky atom, like hydrogen, for example, and these are getting in each other's ways. They're experiencing steric strain. We call this particular arrangement where the two carbons are, looking down the carbons, the two atoms that they're attached to are lined up with one another, directly opposite one another. We call that an eclipsed conformation. So in a sense, one is eclipsing the other. There are three mechanisms by which these molecules can reduce the amount by which these atoms sterically interact. They can increase or sometimes decrease, but mostly increase bond lengths. They could adjust bond angles away from those that are dictated by the VSEPR model. Or they could undergo a torsion about the single bonds between two carbon atoms, for example. The least energy in all of this is required for the torsional adjustment, so that's the one that we're going to see happen more commonly. In order to relieve the torsion that we're showing above, we would have to rotate about that carbon-carbon bond somehow. And for example, if we rotate it a certain direction, we would generate a greater separation between those atoms, and this would, in some sense, relieve the steric strain. When we have this sort of thing where the two atoms are no longer directly eclipsing one another, we call this a staggered conformation. So I want you to remember these words, eclipsed and staggered. Eclipsed, they're directly opposite one another. Staggered, they're separated a little bit. We need to also learn the difference between the terms conformation and configuration. I almost made that mistake a moment ago. Conformations are different arrangements that are caused by motions about torsion angles. So a torsional adjustment would lead to a different conformation. So example, eclipse and staggered, those are two different conformations. Configurations are the shapes of different arrangements of atoms that are structurally different from one another. So, for example, structural isomers represent different configurations. Let's learn about this concept. I'm going to give you a chance to try this out. I've drawn a molecule on the left, dichloroethane, and what I want you to do is decide which of the molecules on the right represents a different conformation and which of them represents a different configuration. I'll give you a moment. Please pause the video so you can work this out. Okay, hopefully you've had a chance to do that. These two are different configurations. Notice that the one we started with has the chlorines attached to different carbon atoms, whereas the molecule on the right has them both attached to the same carbon atom. These represent different configurations of the molecule. The other two, however, are different conformations. We can move from one to the other by simply twisting about that central carbon-carbon bond. That's what defines different conformations. So in order to better visualize these things, we're going to introduce a concept called Newman projections. So we're going to imagine that we're viewing a molecule down a carbon-carbon bond. So we'll start with a molecule like ethylene glycol. This is actually an active ingredient in antifreeze. And we're going to look down that carbon-carbon bond from this direction. So if I reposition that molecule, this is what the system might look like. Okay, you can see that the front carbon atom has its carbon-oxygen bond pointed straight up, and the other two bonds are hydrogens. And then we're seeing the atoms that are attached to the back carbon, but we can't actually see the rear carbon. So how we might draw this is we would first we would draw a circle that would represent the front carbon of these. And then we would draw the bonds attached to that front carbon. You can see as I draw these on the new diagram, I'm mirroring that with yellow bonds in the right-hand side. Okay, so this is what that front carbon might look like. Now, even though we can't see the back carbon, we can see the things that are attached to it. So we draw those as bonds that emanate from the edges of that circle. The one on the upper left is actually attached to an OH. So this resulting diagram is a Newman projection of this picture that we have on the right. Now you notice I didn't actually label the hydrogens. Usually we don't label the hydrogens, we only label the special other things that we see, anything that's other than a hydrogen attached to the carbon. So that simplifies the diagram even further. But the Newman projection gives us a really simple way to diagrammatically organize what a conformation might look like. So let's take a look at this for molecules that have a large number of different conformations. So we need an efficient way to represent this large number. So now if I have an eclipse conformation, I might organize that in a Newman projection as follows. Now notice that I have staggered them slightly from one another, but the eclipse conformation, the two atoms that are eclipsing are very close to one another in the Newman projection. All right, we stagger them slightly so that we can see them. In the staggered conformation, we might draw the Newman projection more like this. And here, the angle between those two atoms that were sterically interacting is 60 degrees. So we've actually rotated that rear thing by 60 degrees. Notice that if we rotate it by more than 60 degrees, we bring it close to the atom on the lower right. So that would again lead to some steric interaction. So when it's staggered, we're generally rotating by 60 degrees relative to an eclipsed conformation. We call this particular conformation a gauche conformation. I'm not sure why it's called gauche, but you should remember that a 60-degree staggered conformation, or a staggered relationship between two things in a conformation, is a gauche relationship. If they are 180 degrees apart, we call this particular conformation an anti-conformation. Okay, let's see what this looks like for ethane. So we're going to look down the end bond of ethane, and this would look something like this when we turn the molecule around. The Newman projection for this would be drawn as follows. For the 1, 2, and 3 bonds, those are made to the front carbon. The 4, 5, and 6 atoms are attached to the back carbon. So this is what that Newman projection would look like for ethane. Now if we look at a more interesting example, difluoroethane, we would look down from the end there, we would see something that looks like this picture, and the Newman projection for this would look something like this. Okay, notice that we have one fluorine straight up, one to the upper left, so these are in a gauche conformation to one another, 60 degrees apart. I hope you've gotten a sense now for what these Newman projections do and how they can simplify how one represents different conformations in a polyatomic molecule.